Hello everyone and welcome to the new lecture, and let me briefly review the last lecture. And as you can see on the screen that we discussed the D'Alembert principle. I'm not going to talk about it because in last lecture we have discussed a lot about D'Alembert's principle, which for dynamic equilibrium. And then because of we cannot put the coefficient of the virtual displacement equal to 0 because the delta Ry is going to be dependent quantity. So that's why we need independent coordinates to put the coefficients of that this virtual displacement equal to 0. So I need that in terms of the generalized coordinate, which are going to be independent. So and then we for this with this ideology we try to build up the Lagrangian for the system, which was defined to be a scalar quantity and a difference of the kinetic energy and the potential energy. Okay, and because the kinetic energy and potential energy are the scalar quantity, so we have the Lagrangian as a scalar quantity. And then we because this is scalar quantity Lagrangian, so we can transform from one coordinate system to another coordinate system. And for that we define that I go from R to my generalized coordinate q1, q2, q3, because R are dependent coordinates, like x, y in are dependent coordinate in case of the simple pendulum, and then theta is independent coordinate, is a generalized coordinate. And then we define this we differentiate and define the generalized velocity. And then when we have generalized velocity we define, and this was my important relation which we have used, if you remember. And then this is my virtual displacement. We calculated the virtual displacement, and applying the D'Alembert's principle, that the work done by the this this force, that is the applied force, minus the reverse effective force times my virtual displacement is going to be 0. Okay, so because we want my system to be in static equilibrium from dynamic to static equilibrium. And then we do a certain mathematical calculation which I have already explained to you, and within that we come across this quantity which is known as the generalized force. So this Q is my generalized force. Qj is going to give the components of the generalized force. This generalized force can consist of applied force, inertial force, and constant for all type of forces, which like this is here. Now then we concentrated on the second term of this equation, and what we finally get is in terms of this kinetic energy T minus T, and then we use that into the final equation, which was my, if you remember this, this was the two part of that Lambert's principle, which gives me this, if you remember, this was Fia minus P dot, and then I have delta Ri, so this becomes delta Qj. Okay, so this component with the Fi component with this gives me this generalized force. Okay, and then this Pi component with this give me this quantity. Okay, so taking Qj, delta Qj common, what we have is ddt of this. And because now we, with the argument, because if you remember we started with that delta I, which was earlier, that was delta R, which was not independent coordinate, that were dependent coordinate. We move to this delta Qj, which is now my generalized coordinate, which is independent quantity. So now I can write this this coefficient equal to 0. So that's why we have this particular equation, which is known as the Lagrange equation or Lagrangian equation, which give me different equations of motion depending upon what are my generalized coordinate. But here we have my force, generalized forces. So till now we have we had covered this in the last lecture. Now let's move to further with keeping in mind this Lagrangian equation. So my, because in that Lagrangian equation I'm having this generalized force. So if my force in the system is conservative, because and if the force is conservative, we know that that force is can be written in terms of the potential, and that that potential, if I take the gradient of that potential, I am going to give that conservative force. This we had already discussed it. So this Qj, which is my generalized force. Now let us try to write it in terms of, because now I suppose this is my conservative force. So this which the relation of generalized force is force times delta R delta Qi, and this force is putting against this force. This is coming from this potential V. This is my gradient. If you remember, gradient is nothing but this differential operator del del x plus j del del y plus k del del. This is my differential operator, if you remember. So and this I is like it is acting on the ith particle, okay, whose this R is given, because R ith is xi I plus yi j plus zik. So this I is for the ith particle, position vector of the ith particle, x component, y component, j component. So this is going to be corresponding potential which upon this, and this whole expression is can be written as dv by del qj, because this is equivalent to partial derivative of the potential with respect to qj. So if I have my potential v, which is depending upon r1 r2, so this is r1 r2 r3 up to n, and to Rn and T. So basically this depends upon R and this is T. So if I take the partial derivative of this with respect to Q, so this is going to be V with respect to, because it depends upon R del R, and then del R with respect to del Q, okay, and then because it depends upon T also, so let's this is going to be delta V by delta this is delta V by delta T and delta T by delta Q. This is nothing, so because velocity is not depending upon this. So overall what we have is this thing, and delta V by delta R is basically this quantity, and delta R by delta Q is basically delta R by delta Q. So I can write this quantity as a partial derivative of the potential which depends upon R. This potential depends upon R with respect to Q. So when we put this, if you remember the expression that d dt of delta qj, so if I have say this is my earlier expression, d dt of delta t by delta q dot j minus delta t by delta qj, that was equal to qj. So now my qj, if I put in place of qj this delta v by delta q, so this is going to be minus delta v by delta qj. So I can take this on this side and with negative of v, so this is t minus going to be v and delta qj, okay. So my Lagrange equation is now this thing, and I have t minus v here. The second important thing in this equation is going to be the potential, because now the potential is entering with the force. So if the force, earlier we have the generalized force, now we know that generalized force is like if conservative, we can derive it from the potential. So now the force is now replaced by the potential. This is kinetic energy, and then we take into place the potential energy. Because why we are doing this, because you know that when we had to formulate the Lagrange equation of motion, and you know that L is basically kinetic energy minus the potential energy. So that is this is what we are trying to do mathematically. Now this V, the potential is like here you can see potential is now depending on the position coordinates only, not the velocity. So till now we have assumed so the applied forces are conservative, and because these are conservative, so it depends upon endpoints, path independent, and all these things. So the corresponding potential is naturally is going to be the function of the position coordinate only. This is V is going to be depending upon the Q, the generalized position coordinate only, but not on the velocity. Okay, so but if also depend upon the velocity, that is generalized velocity, that is q dot, okay, then in that case which are going to be some special cases, then my generalized force in term which we can derive from the potential is from the potential part, which is depending upon the position coordinate, and then the potential part which depends upon the velocity. So my q is now having two parts, that is one depending upon the potential as well as depending upon the uh, potential which depends upon the coordinate, and then potential which depends upon the velocity also. So now if we consider the potential v is independent of the generalized velocity, that this is the general case where we can have the potential is also depending upon the velocity. So if this is not depending upon the velocity, only depending upon the generalized position, then this potential partial differential of the potential with respect to the generalized velocity is going to be zero. So if this is so, then I can uh, add this term into the time derivative. Okay, so you see that here we have this term. So we have d dt of only the kinetic energy term is there with this velocity, generalized velocity term. Now if I write this as t minus v, and because we know that v is delta v upon delta qj is independent of time, so that it's not depending upon the time, this is zero. So safely I can add this term, this delta v by delta qj, which is going to be zero considering v is not depending on the generalized velocity. I can safely introduce into this equation, and because we know that this quantity t minus v is going to be the Lagrangian of the system in which the conservative forces are acting, and those conservative forces are derived from the potential, which are the function of the position coordinate only in terms of the generalized coordinate. So we finally lead to this equation, that is my t minus v is becomes here L, and this become here L, and then I have this equation which is known as the Lagrange equation of motion. Okay, so you can derive the Lagrangian equation of motion. What we have done is we have actually derived the Lagrangian equation of motion starting from the D'Alembert principle, the condition that the applied force is Fi A minus P dot I, and delta, say that delta Ri is going to be zero, and we transform this from generalized like Cartesian coordinate to dependent coordinates to the independent coordinates, and then finally we get this Lagrangian equation of motion. So earlier it was, if you remember, you have this part was having my generalized force, and that depending upon generalized force, if the generalized force is derivable from the potential or not. So more generally, if there may be cases that this qj is consisting of all sort of forces, but beside conservative forces there may be some other forces. So what we have zero, get zero here, because those conservative forces are derivable from the potential. So that potential is like taken care into the Lagrangian of the system. But irrespective of that, what forces which are left behind, which are not derivable from the potential, that has to be taken care if there is some, and then this equation is now this place, we at the place of zero we have to have this qj, which are now consisting of those dissipative forces, like the most is one example is the frictional forces. So all the dissipative forces are, if there is in the system, then I have to use this Lagrangian to work out the mechanical system under constraint. If there is no certain dissipative forces, we are only concerned about this conservative forces, then this equation is well enough to calculate the equations of motion of the mechanical system. Okay, I think this is clear till now, and for the Lagrangian part, and then we move further to discuss something about what because when we are doing the Lagrange, calculating the Lagrangian, and we have already come to the central part of our course, writing Lagrangian, and then we will move from on the basis of Lagrangian to the Hamiltonian dynamics. So what is this basically is? So when you are doing the Lagrangian calculation, because this is in terms of, we are going to do L equal to t minus v, you are going to do this equation, that is the dt of delta Lagrangian and then q dot generalized velocity L and dq equal to 0. This could be, or some q dissipative forces. So in order to handle the mechanical system in Lagrangian dynamics, we are going to use this equation. Like beside that, we in Newtonian dynamics we have many equations of motions which are there. S is equal to ut plus half at square, v is equal to u plus at, and v square u square 2gs, and all these there are projectile motions made. So there are different equations, differential equation f is equal to dp by dt in Newtonian dynamics, through which we calculate a certain problem, mechanical problem. But the Lagrangian dynamics does not constitute some new theory, because in fact this is a new theory, but what we are going to the final obtain the final equations which governs the mechanical system, particular mechanical system which is under study. So either you do through the Lagrangian dynamics or through the Newtonian mechanics, must be the same for any given mechanical system. Okay, they are not going to be different, because finally what because yeah, mechanical system, it is behaving and its prediction and its motion and acceleration, velocity, energy, all these things, whatever dynamics you apply to calculate and to predict has to be same. So either you do the Lagrangian dynamics or the Newtonian dynamics, or the in further we're going to do in Hamiltonian dynamics, the end result is going to be same depending upon what method I am applying. Like in Newtonian mechanics, what you apply, and this is you apply the force from the outside. Most of the cases the internal forces are not there, and then constraint forces, frictional forces, resistant forces, or dissipative forces are there, so acting on the system. So we concerned about this forces acting on the system. We equate those forces, and then we try to calculate, solve those differential equation depending upon the Newton's law, and then we get what is the position, what is velocity, what is the acceleration. That is what we do in Newtonian dynamics. But in Lagrangian, what we are going to do, we are not bothering about this force. That is, I'm bothering about this Lagrangian, which is T minus V. So if I know system's kinetic energy and the potential energy, which is these are the two quantities which are associated with the system, then I can build my Lagrangian. Okay, and what are the forces are acting on the system? If I know the kinetic energy and the potential energy, I can very well build the Lagrangian, and I can predict the equations of motion for that particular mechanical system. And this concept of the energy which we are using in Lagrangian dynamics is important, because it becomes a scalar quantity, because kinetic energy and potential energy are a scalar quantity, and the quantity Lagrangian itself is going to be a scalar quantity. So any scalar quantity is going to be invariant under the coordinate transformation. So it is very important that when we have a free hand to work into any type of coordinate system where we find ourselves to solve those differential equation in an easy manner. So the transformation are not basically restricted between various orthogonal coordinate system in ordinary space, like going to Cartesian space to a spherical polar coordinate or cylindrical coordinate, but we can also go to one space, our physical space, to the configuration space, because we had already discussed this physical space and coordinate space, this generalized coordinate span space, which is the configuration space. So that is important, because in doing this mathematical simplification, so whatever system I'm going to do, if my calculation is going to be maximally simplified, then I'm going to be a happy person to solve that mechanical problem. So this is important aspect when you are doing something, trying to solve some mechanical problem. And then force versus energy viewpoint is that in certain situation, because if you are dealing with some mechanical system, it is not necessary that I'm going to understand all sort of forces are acting on the system. I'm not going to figure out. If I'm not going to figure out, but I know still that what is the energy, what is the kinetic energy, and what is the potential energy. Or maybe only the kinetic energy is there, there is no potential energy, or I don't know the force exactly. So then by just knowing the energy of the system, I can have the Lagrangian, and once I have the Lagrangian, I can write the equations of motion, I can solve it, and that is going to give me all sort of prediction and uh, related physical quantity for that particular system. So that is knowing the energy, because Hamilton energy domain, when you do some calculation in energy domain, that is going to be the Hamilton principle, and that is basically very helpful when you do the quantum mechanics, where you only know the energy of the particle in terms of the field or in quantum field theory. So that is going to be very helpful. That concept of uh, energy based solution is very important to help those mechanical those system where we don't know actually uh, the forces which are acting. If you go to quantum size, quantum level, then if you're not considering all those forces, you know the energy, then you can solve all sort of equation depending on writing Lagrangian, Hamiltonian, and all these. So now we know that Lagrangian is a scalar function, and it is going to be invariant with respect to the coordinate transformation, all sort of coordinate transformation there are. But the important thing is that whatever the coordinate space you are transforming or adding or deleting to the Lagrangian to the system, but overall, if it's going to leave my equation, Lagrangian equation of motion, unchanged, then that transformation is allowed. Anyway, this is a scalar quantity, is going to be invariant, but if you are adding or deleting something, some part, you're doing something with that, the Lagrangian, who is going to give you the equations of motions, and then by doing this, if you're not going to change the equation of motion finally, then that those kind of transformation are allowed. So let us discuss one uh, part, which is this is one example that if I have a Lagrangian, this is my Lagrangian, which is say this is my Lagrangian, existing Lagrangian, which depends upon the generalized coordinate and generalized velocity and time. If in this Lagrangian I'm going to add a function f which depends upon q and t, and this is a differential function. If I add in this Lagrangian the total time derivative of this function, so I'm going to get a Lagrangian which is L prime. This is my new Lagrangian for a function fqt, which is a continuous, having continuous first and second order partial derivatives. So the function has to be continuous. This is important. So let us see whether the new Lagrangian is going to change the system or not, going to change the equations of motion or not. So if you have this Lagrangian L, for this Lagrangian, this old Lagrangian L, what is going to equation of motion? That is d dt of L by delta qi dot minus delta Ly delta qi, and this is going to be 0. This equation, Lagrange equation, and through which we get equations of motion for a system through for which I am writing the Lagrangian. So now L prime is my new Lagrangian. So for that, the equation, Lagrange equation of motion, is going to be d dt of delta L prime delta q dot delta L prime delta q is going to be 0, in analogy with the Lagrangian equation of the old Lagrangian L. So now let us calculate this term delta L prime delta qi, because this L prime is here. So the first term will be delta L upon delta q, and the second term will be delta q partial differentiation of this function d dt of q prime. Okay, so this is what I have, and then the second thing we want is this one, this term L prime with respect to q dot. If I differentiate this L prime with respect to q dot, so I have L prime with respect to q dot, so I have L with respect to q dot, and then this function, this addition term with respect to q dot. These two things I need to see that whether I fulfill this equation of motion or not. So for this function fqit, so this is d dt of fqit. So this function which I have added to the old Lagrangian. So if we see that if we figure out d dt of Fit, because f depends upon q and then it depends upon t. So first we partially differentiate this f with respect to q because it depends upon q, and then q with respect to time, and that gives me the q dot. Okay, and then this f with respect to t. Okay, and then t with respect to t, that is going to be f with respect to t, and then there will be t with respect to delta t. This is going to be 1, so this is going to be 1, so I'm just having this equation. And then I have to take delta q dot of this quantity. So this we already know is this thing. So if I take delta q dot, so what I'm going to do is partial differentiate this quantity with respect to q dot. So q dot only comes here, not in this, so this is not going to contribute. So with this q dot, the term becomes delta q of fq dot, because I'm differentiating over q dot. Fine. So this term is here, and now I have to take what, because the time derivative of delta L prime and delta q dot, because this I have to take. So delta L prime of delta q dot is this thing, so I have to take the time derivative of this. So I'm going to do the time derivative of this d dt of delta L prime delta q dot I, because I'm going to get the time derivative of this particular expression. Okay, so this is del d dt of delta L prime delta q dot. So you see that so first term is delta L upon delta qi dot. So I have this d dt of delta L upon delta qi dot, and this second term is this, I'm going to write d dt of delta q dot of dtfq. So this I have already calculated, which is this thing. So this is not just was d dt of this delta qi of f function. So that is going to be d dt of delta q fi q dot. So now I write the Lagrangian equation for this L prime, the first term and the second term. The first term comes out to be this d dt of delta q, and this second term is this, and then minus del L by del q prime, and del L by del q prime I have already calculated here is this thing. If I put into here, so you see this is first term and this is the second term. So now let us rearrange this. So I have this first term here, this one is already here, d dt of delta L delta q dot, and then from here by this term I have here, and then now I again this term here, d dt of delta q fqt, and then this term here. Okay, so now differentiating these two terms independently, so that you can see the structure of these. The Lagrange equation, how you write the Lagrange equation, d dt of delta L by delta with respect to q, and then delta L with respect to delta q equal to 0. So you see the same equation here, d dt of delta L by delta q dot and delta L by delta q. This is the Lagrangian satisfying. This is my old Lagrangian which is satisfying the Lagrange equation of motion. So this is going to be 0. Okay, so according to this Lagrange equation of motion, and then this is d dt of delta fq upon del q dot, and this is d delta q of, in you see if you replace L f by qt here, so what you get, Lagrangian equation of for this function f. So this is also going to be 0. This is Lagrange equation of function f. So this is also going to be 0. So finally this term, first term is 0 and the second term is 0, and then your Lagrangian equation of motion is for this new Lagrangian, which is L prime equal to L plus d dt of a function qt, which is differentiable. So if you add the total time derivative of a function which is differentiable into the Lagrangian, and then the new Lagrangian is not going to change the equation of motion. So this kind of transformation is allowed because when you add a total time derivative of a function which is differentiable and which is continuous, first and of second order continuous differentiable function, if you add the time derivative of this to your Lagrangian, then you get a new Lagrangian, but this new Lagrangian is also going to give you the same Lagrange equation of motions. So that is that transformation is allowed, and whatever this type of so you have a leverage that you can add, you can modify your Lagrangian to simplify the calculation. If you have if you can add a certain function which is a total time derivative of that function, which can change your Lagrangian and to ease the calculation, because this is not going to change the final equation of motion for the mechanical system. You are doing this. Okay, then let's move further for this. So I think time is enough, and then I'm not going to start the new topic. So in the next class we will start from the kinetic energy in terms of the generalized coordinate, because we have figured out now from starting from the D'Alembert principle, we have written the Lagrangian by transforming my coordinate generalized coordinate from dependent coordinate to the independent generalized coordinate, and we see that the condition that if the forces are conservative or potential, or whether the potential is coordinate dependent as well as the potential is velocity dependent, then finally I'm going to get a Lagrange equation of motion. And we discuss about the essence of the Lagrangian formalism, and which is important, which is giving you a new tool to describe the system. It may possible that you're not going to get as simplified as equation of motion as you do that particular problem in terms of the Newtonian mechanics. When you do it in Lagrangian dynamics, so maybe you're going to get a complicated equations of motion. So it is better to choose the Newtonian dynamics, depending upon if you have a leverage to either your generalized coordinate are also in physical space, as well as the generalized coordinate is also is having in your configuration space. And then we figure out that if I modify the Lagrangian with a certain function, if I add the time derivative of that function which is continuous and differentiable, then that particular Lagrangian transformation is not going to change the equation of motions. So I think this is all for this class, and then from the next class I'll start the new topic. Okay, so thank you very much.